Titration of a weak acid with a strong base. So this is a multi-part problem. We're on 1A. What's the pH of 50 milliliters of 0.10 molar acetic acid? We set up an ice table. We have our weak acid in equilibrium with hydrogen ion and acetate. Initially, we have 0.10 molar acetic acid, 0 hydrogen ion, 0 acetate. We look at the forward direction. So we have minus x plus x plus x. That gives us our equilibrium. We set up our equilibrium expression, and we have our products over our reactants. We use the Ka of acetic acid. We're going to simplify, assume this x is small, and so we will use this as being equal to the Ka. Solve for x. X is our hydrogen ion concentration. So once we get the hydrogen ion concentration, we use the pH equals minus log of our hydrogen ion concentration, and we get this pH. So this pH is before any base has been added. So if we look at our system where we're doing a titration, we would have a burette. The burette would have base, so let's use sodium hydroxide. The acetic acid would be in the Erlenmeyer flask. And at this point, no base has been added. So the pH is due to the dissociation of the weak acid. So if we look at a pH curve, we would have 0 base being added. Okay, so now we're on 1B. What is the pH of 50 milliliters of acetic acid and 10 milliliters of sodium hydroxide? We need to set up a table to react the weak acid with the strong base. Since sodium is a spectator ion, we can ignore the sodium. And then the reaction will go to acetate plus water. So first, we want to calculate the moles we have of the weak acid. We multiply the volume. We take the milliliters, change it to liters, multiply by the molarity, and that would get our moles of acetic acid. We do the same for the base. We take the milliliters of base, we convert that to liters. We use the molarity of our base. We multiply those, and that gives us moles of our base. So now that we have the moles of each, we will subtract the limiting reagent, which in this case is the hydroxide. So the acetic acid will subtract 0.00100 moles. We'll subtract 0.0010 moles of our base, but we're going to add 0.0010 moles of the acetate. So the limiting reagent is the hydroxide. That's how we get 0 for the hydroxide. When we subtract the limiting reagent from our acetic acid, that's how we get the moles of acetic acid. And then we're gaining product, so that's how we get the moles of our acetate. So we are adding 50 milliliters to 100 milliliters, which is how we would get 60 milliliters. And that is our total volume. So remember, you want to use the total volume when you calculate your molarity. So now we get a final molarity of the acetic acid when we do the calculations. We get a final molarity of the acetate. And now what we're going to do is we're going to use the ICE table. So this is the typical ICE table that we've been doing all along. So we have our molarity of acetic acid. We have 0 hydrogen ion. We have molarity of acetate. We have minus X plus X plus X. We get our equilibrium. We set up our equilibrium expression. This is the same acid, so we use the same value for the Ka. We're going to assume this X is small, so we can simplify the equation. We use the 5% rule. We solve for X. And then remember from our table here that the X is the concentration of hydrogen ion, and that's how we get the pH. Okay, this is the same problem, but now we are on 1C. So we still have 50 milliliters of acid, but now we have 25 milliliters of our base. So we take the volume of the acid times the molarity of the acid. We get the moles of the acid. We take the volume of the base times the molarity of the base. We get the moles of the base. We subtract the limiting reagent from both. So we're losing acid, we're losing base, but we're gaining acetate. We get the final moles of the acid. The base is all used up, so that is 0. We get the final moles of the acetate. We add up the volumes, so 50 milliliters plus 25 milliliters. That's how we get 75 milliliters, but then we convert it to liters. So then we can get the final molarity of the acetic acid, the final molarity of the acetate. We can set up the ICE table just like we've done before. And so we have our molarities of acetic acid. We have our change. We have the equilibrium. So now We set up our K expression. We simplify, use the 5% rule. We solve for X. X is our hydrogen ion concentration, and then we can get the pH. So we have added some base, so the pH is going up a little bit on our titration curve. Okay, we are on the same problem, but now we're on 1D. So we have 50 milliliters of acetic acid, 50 milliliters of our base. We calculate our initial moles. And in this case, when we subtract the moles, we end up getting 0 acetic acid. Acetic acid is all used up. We end up getting 0 hydroxide. Hydroxide is all used up. But we do have some acetate. So we will take our 50 milliliters of acid and add that to our 50 milliliters of base, and that's how we get our total volume. And we can calculate the molarity of the acetate. So right now we have 0 acetic acid. We do have some acetate. Acetate can act as a base. It's a weak base. We can set up an ice table, but this time we're going to use acetate and react it with water. So we have acetate plus water in equilibrium with acetic acid plus hydroxide. We do have an initial molarity of the acetate. Initially, we have 0 acetic acid and 0 hydroxide. We're going to consider the forward direction of the reaction. So minus X plus X plus X. That gives us our equilibrium. And then we need to remember that the acetate is a weak base. So we need to use a Kb. We use the Ka of acetic acid times the Kb of acetate equals the Kw. We use the Ka value of acetic acid, so we can solve for the Kb of acetate. We get the Kb of acetate, and now we can use our ice table. So we have products over reactants. We're going to assume this X is small and make an approximation, simplify the equation. So we can solve for X. And then remember, in this case, the X is our hydroxide concentration. So we can use the hydroxide concentration to get a POH. Once we have a POH, we know how to calculate a pH from that. So we are still on the same problem. So now we have a 50 milliliter solution of acetic acid and 60 milliliters of base. So we take the acetic acid, react it with the base, and then first you want to calculate the moles of acetic acid. We calculate the moles of base. So again, that is volume in liters times the molarity. And this is the same acetic acid we've been using for all the other problems, which is why it's the same molarity. We get the moles of acetic acid, and in this case, the acetic acid is the limiting reagent. So we subtract the moles of acetic acid and get 0. We subtract the moles of acetic acid and we get a moles of hydroxide. And we're adding to our product. So we get a moles of acetate. We add our volumes together. So 50 milliliters plus 60 milliliters. That's how we get the 110 milliliters. We put it in liters. So in our table, we get a final molarity of hydroxide and of acetate. So now we're going to set up the ice table. So the ice table is acetate reacting with water to give acetic acid and hydroxide. So from the previous table, we put in our molarities. We have a molarity of acetate from the previous table. We have a molarity of hydroxide from the previous table. And we see that we have no acetic acid from the previous table because that was all used up. That was the limiting reagent. So we are going to look at the forward reaction. So we have a minus X plus X plus X. We subtract the X to get our equilibrium for the acetate. We add the X, we add the X. Acetate is a weak base. We must use the KB, and we had calculated the KB in the prior question. We put the products on top, the reactant on the bottom. Assume this X is small and use the 5% rule. So when we do this and we solve for X, we get this value for X. Now you want to always remember to refer back to your table and see what you were supposed to do with that X. So if we look at the table tells us we need to add X to 0.00909. We'll look at the X. It's 2.94 times 10 to the minus 9. When we add that to the 0.00900x, it doesn't even change this value. So what that means is that this is your concentration of hydroxide. You use that to get your POH, and then from the POH, you can get your pH. So again, this has been all one problem, but these are the steps that you're going to see in a typical problem of any weak acid plus a strong base.